Welcome to my poster presentation, and my dissertation is on network computing. We look at a problem where a network consists of a graph and a set of sources and a receiver node. The receiver wants to compute a target function f of the source messages. We allow for block computation where sources send messages of vector length k and the edges carry vectors of length n, and define a capacity to be the supremum of all ratios k over n such that a k and network code exists. And similarly define a linear computing capacity and routing capacity by restricting the node operations. With this model, we look at bounds on this computing capacity. Use results from communication complexity to define a measure of network connectivity with reference to a target function f and a network n, and call it a min cut nf. And we show that the min cut is an upper bound on the computing capacity for arbitrary networks. And it turns out that the min cut is actually equal to the computing capacity as long as the network has a tree-like graph. And for arbitrary networks, we provide lower bounds based on Steiner tree packing algorithms, as well as by embedding a given function into a linear function space and then use results known for linear functions. The results are summarized here, which compares the tightness of this min cut to the computing capacity. And it turns out that for some function classes, the min cut is a close measure of the computing capacity, whereas there are example functions, including an arithmetic sum function, for which the bound might be loose. And then we move on to the study of linear network codes for computing. And it turns out, and then we define a subclass of functions called linear reducible functions, and which basically mean that we can project a source vector into a subspace using a projector operator t, and then compute the function from the projected vector. And it turns out that the linear codes may provide a capacity advantage only if the function f is linear reducible. And for functions that are not linear reducible, linear computing capacity coincides with the routing capacity for all networks n. We have some results related to that, and that are summarized in this following Venn diagram, where we show that coding gain always exists for non-injective target functions, but linear gain only exists for linear reducible functions. And in fact, for a subclass of the linear reducible functions, linear codes are optimal. And moving on to the study of functions which are a subclass of linear reducible functions, we provide a Grosvenor basis characterization of when a linear code exists for solving a network. It turns out that by defining an appropriate ideal J, a linear code exists if and only if the Grosvenor basis is not equal to 1. And using this characterization, we identify a subclass of functions for which linear codes are sufficient for solvability, and another subclass of the linear functions for which linear codes may not be sufficient, even though the min cut may be sufficient. And the other research contributions include the study of computing problem over noisy networks, where we used a binary symmetric channel model proposed by Gallagher, and study of random matrices over finite fields, where we looked at design of matrices by randomly choosing entries such that each of the submatrices are full rank. And then we also looked at energy efficient multicast for wireless networks. That concludes my presentation. Thanks.